our last sessions, we looked at the electrodynamics. We were looking at the generator and the dynamo, remember? And we had the split and the slip rings, and the one gave us a sinusoidal, and the other one gave us a curve that did that, correct? An output waveform that looks like that. And we said that we looked at the ends of the things to see what the polarity, the plus and the minus on the brushes was going to be. Now, what we now need to look at is we're going to be looking in the first section on the dynamos and generators. Remember, we supplied an external force. So we turned the handle, or we shook the magnet through the coil, or we had a motor on the side that was burning a fossil fuel in order to turn our coil in between the magnets, right? So what we had is we had our magnets, and I think I've still got south and north have changed places now. So we've got north and we've got south, and we had this, and we turned it, and we generated a flow of current. Now, what we're going to look at next, we're going to look at those, they're going to come back into play, don't worry. What we're going to look at now is we're going to look at what about if there's a current flowing. So we're going to look and we're going to say, what if there is a current flowing in the conductor, right? Now, you remember that if we had a current flowing in a conductor, let's say we had that, the current is coming out. So you put thumb in the direction of the current, and the fingers show you the direction of the magnetic field going around it, correct? Like so. There we go. So our magnetic field is like that. What if we had another one over here also coming out at me? Let me change the color and make it, well, let's make it blue. All right? Blue, I put my thumb and the fingers tell me the direction. So I have these guys coming around like that. Now what do I do next? We've got a bit of a problem because these two wires here are both carrying a current at me. Remember, the tip of the arrow is at me. What happens here? Let's just examine over here. I have got a magnetic field coming up here, right? And I have got a magnetic field coming down here. What happens when they meet? Well, first of all, you can quantify the magnetic field, and they act in a direction. Therefore, they are vectors. In essence, thus, the two are going to cancel each other out. Because if we've got the current flowing in the same direction, the magnetic fields are going to clash in the middle. So what do we end up with? We end up with something that looks like this. We end up with a magnetic field, a current coming there, a current coming there, and a magnetic field coming this way around and going that way around. But in the middle, we have zero magnetic field. Which means if we have zero magnetic field, okay, in between these two, right, what's going to happen is this. This is going to be pushed with a force towards each other. We can quantify that. It's not part of what we do currently. We'll do that in the A-level section or the university section. Now, so basically what we're saying is they cancel, so there is a force between them that tends to push the conductors together, right? So this pushes together, right? Well, that's pretty obvious. We can work that out from first principles. There's very little magnetic field in between, so these two wires get pushed towards each other. What happens if we've got one coming up this way and that one is going in? Well, we draw our magnetic field going around, and this magnetic field, I'm going to draw in blue again like I did, that's going in, so the magnetic field is going that way. Can you see that they add together here? So you're trying to get more flux let's just think about it. Between here, you're trying to get more flux lines, right? The net result is that you have a buildup of flux in between, and you have these two guys being pushed apart. Pushes apart. A force and a force. Right? So, what we're saying here is that, and you also know it, that a magnet can create a force. You can pull or push things with a magnet. I mean, here are my sort of favorite bits and pieces of toys. Look, you can see it actually pulls and pushes, and you can feel the magnetic force between it. So what are we saying? We're saying that these current carrying wires experience a force. Now, let's take it a next step further, shall we? Let's just check that we go about the next one. Okay? Let us say that we have, just make sure that's changed. Let us say that we have a current wire that way, and we have a magnetic field going here. All right? Now we have a current. So we have a current here. All right? We have a current, which means what? Which means that now it's no longer applying a force. We have a current. Which way is the force? Or the movement? Now, we now say that we have to use Fleming's left hand. Fleming's left hand motor rule. Okay? LHM. Left hand motor. All right? No, I don't know a mnemonic. Okay, we'll try and find one. All right? So, basically, what we mean, we've got a current, so we must use Fleming's left hand motor rule. All right? So we say, all right, now, left hand motor rule. Right, let's see. What have we got here? Thumb. M gives motion. Okay? It gives the direction of the force. Okay? Forefinger is the field again. And lastly, but not leastly, is we've got our second gives the current. Okay? So let's recap. Field, okay? Left hand motor rule. All right? Right hand dynamo, left hand motor. So we say, okay, field, right. The field is going that way, which means north is there and south is there somewhere, right? So now we've got the current, and the current is going into the page, right? Field is north to south that way. So it's actually this. We've like got magnets there, right? And we've got a current carrying wire going there. So we've got that, and the current is going down. And if the current is going down, the force, okay, on that wire is going to be, all right? Sorry, current's coming out the page. What am I talking about? I'm thinking of another one. The current's coming up. Sorry. The current's coming out of the page, right? The force is that way. Sorry, the field is that way, current that way, so the force is up that way. Okay, let me just go through that again. Okay, I was totally dead my cart. We've got the field going from north to south, all right? We've got the current coming this way, which means the motion or the force is given by that. So if I'd have to actually stand it up like that to show you, but can you see, if you look at yours, you've got the current coming out, the field that way, the force is going to then be up, all right? So the thumb gives the motion or the force, all right? The forefinger is the field again, all right? Just get it back to black. It's the field again, and the second C is the charge, the current that's moving. All right? So on these problems, you can see it's going to be the same as these. You're going to be given 2 out of 3. All right? Now, let's move along a little bit and say, okay, we've got that. The wire is pushed upwards. All right. Okay. All right. Okay. 2 fields interacting with vector addition. Okay. Same thing. All right. Now the motor, the field, the current, the thumb, okay, you may see it like this, THUMB, that is the thrust. There's another one, all right? If you want to leave out the motion force, the way it's being pushed, you can do thumb and thrust. Okay, it's another way of looking at the same thing. So what we've got, you've got thumb for thrust, right? Now let's have a look at this guy. The difference previously we turned it. Now we're going to run a current, okay? I'm going to run a current through that thing. So let's just look. North, let me check, is there. North to south, I've got a current, so it means that we have to use the left-hand motor rule. So there it is. The current is running from A to B. Now, if it's running from A to B, okay, it means that field, there's the field. Current is running that way. Therefore, this wire will be forced down like that, right? Let's try it again. Field is that one. Current is my index, my middle finger, second finger, that way. So the force is actually down. Let us draw it. All right. Let me draw it. Okay. Again, as best I can. Whoops. Let's draw this thing. We say, all right. Right. Go back to there. Let's put in a north and a south. Right. So the field is that way. Right. That's the field. So now I've got my loop. Let's put it in 3D. Right. I've got my loop coming up like this. All right. The difference we said is we've now got a current in it going that way. Right. Very often the off-putter here is the whole three-dimensional aspect. Right. So we've got a current I. There it is. Okay. We've got the current and it's I. Okay. Come on. It is there. I. I is running that way, right? So we say, right, field, north to south. There we go. Current is going that way into between the magnets, which means that the force acting on this guy is a force down, right? So we are being forced down. Now, when we look at this, let's look at the other side. I'm going to label them A, B, C, D again. A, B, because we're used to it. Let's look at there. The current is going this way, right? North to south, current carrying out, which means this force is going to be up. Correct? Current coming out at us. It's coming out here. North, south is there. Current coming out. Remember, you split the two wires, which means this one is being forced up. This is down and that one is up. So this motor is going to turn that way. Okay? If we do the current in that direction. Everyone should be happy with that. Now, what are we actually saying? We're saying that therefore it's rotating counterclockwise. That is what we're going to say about, because you're going to be asked which way does it go. And you will say it's counterclockwise or it's clockwise. Okay? Now, a motor, all right, basically has got to have a split ring here. All right? Why? Well, because if you look at it, just for the moment, if we have a split ring like that, it means that this is always plus and that's minus, which means the current is going to flow out and back that way. Because if, let's examine this just conceptually. If we put in, can you see that it's got that? Because it's a DC current, right? Going through the motor. If it was an AC current, it means the current goes this way and then turns. So what happens? Well, north to south, current going that way, the force is down. Then the current changes this way, force up. The motor is going to be going boing, 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 boing. It's not ever going to turn cleanly, is it? Okay? So that is why we need to have this, because coming from here, it means we're always going to have a current flowing through the loop in the correct direction. Okay? That's important for us. Yes, of course, you can have motors that are linked to AC, but for the purpose of what we're looking at here, we're saying here's our little split rings. Okay, remember, it's a split ring because it is taking DC. Right? So we've got that, and it's being fed into our wires like that. That's the key part, all right, of this. We're saying, okay, so that it stays positive and it stays negative, all right. Obviously, we've got the current reversing, it mustn't turn. Okay, now let's follow our motor through a series of steps, shall we? All right. Just like we did with the dynamo and the generator, we're going to follow our motor through steps. Here we've got a north and a south, all right? Same as we've got there, and I've got over here a positive and a negative, and I've got my coming in over here like that. These are the brushes. Let me move this a bit closer. Negative there, right? So this is basically going to have a current flowing that way and this way, isn't it? And what is going to happen? Okay, this is going to turn because there's going to be a force on it, and we've said already north to south, current that way. So my force is going to be down, and that one's going to be up. So it's going to turn that way, right? What happens now as it turns? All right, let's go back to there. Okay, north, south. Now we've got here and here, okay, plus and minus over there. Now it has turned like this, all right? So essentially, we've now got our ends are up there, correct? Now at this point, there is zero force, right? There's zero force because why? There's no current flowing. Can you see it? There's no current flowing because it's not touching the brushes. The brushes are on each side. Sorry, these are my brushes here. Okay, let me just get my thing down here. These are my brushes over here. Right? So it's not touching. It's turned already. This side, I had mine like that, and we had our there like that. Now it turns around. It's come to that point. Remember, it's gone this way. The current is still flowing, but there's no force, right? So it goes past that gap just because it's got enough momentum and speed. It's got enough, basically, angular momentum to take it through the gap there. Then it goes around, and where we are is it goes back to the other side. All right? So we go, we say, right, then we've still got the north, we've still got the south, but now we've got, okay, there's the one brush, there's the other brush, this is plus, this is minus. Now you've got your two rings over here that have come through, but now remember what has happened. Let me just go back a bit. Oops. Just go back up a bit. Okay. Now remember, we had A, B. Now we have A, B. So B is now going to the positive brush, right? So what have we got? We've got B, sorry, that's D, isn't it? Don't worry. Let me just keep it the same as last time. Let's make that D, hey? Because that's end D, remember? D and D. So now we say, right, that's D is now on this side. And A is there. And you can see the current is still running in the same direction. Right? It's still running from D now to A, which is actually keeping the motor turning, but in this case it's going that way. Right? So they're actually very simple, aren't they? So all we do, and it continues the anti-clockwise rotation. That's all that's happening here. All we've done is the ends have gone here. The current was that way. Force down, force up. Turning it, no force. Over here now. Now remember, this one has now come to positive. There's A, right? A has now turned this way, this way. A is now touching the negative. D is touching the positive. So as it's turned, we're keeping the current flowing in the loop in the same direction. That's what we're doing all the time. That is why our motor works on a DC. Right? Now, oops. Okay. Let's have a look at this now. All right. So we say, all right, what happens now? What are the factors affecting the power of a motor? Okay. Factors affecting power of a motor. Guess what? It's the same thing. 1, increase magnetic field. 2 is increase number of coils. Increase N, number of turns. Right? Number of loops. Number 3, it all comes back to the same. In this case, it's increase I, the current flowing. Okay? In other words, increase the number of amps on the motor. And 4, more magnets. Okay? So basically, that's the same kind of things as the generators or the dynamos. Similar problem. How do I put more magnets? Do this and put magnets up there like that, so that it's continuously in a magnetic field. All right? That's the way we do that. Now, all right, let's have a look at, can we get a motor running on AC? All right? Let's just go and look at this. An AC motor. All right? Can we get it? Instead of we use the slip ring. Okay? In essence, that is a washing machine motor. We don't go into the details, but yes, you can have it. Okay? Many washing machines are like that. A car starter motor. You've heard of that term before. A car starter motor. All right? That uses DC. Why? It's connected to the car battery. Okay? What have you got? You've got a motor inside there connected to the battery, right? The battery, the moment you turn the key, a current starts flowing through all of the loops. And there's lots of loops in a starter motor. It flows through all of these loops. It's between magnets. That's why it's heavy if you pick it up. And as it does it, it starts to turn this motor, right? Which then turns the engine over to get the first spark going. The moment the first spark goes, it ignites the gas in the combustion chamber, and you can blow the first piston down, and you can start turning the engine. Then, okay, it changes, and you start charging the battery. So the engine actually charges the battery. Okay, it's a mutually beneficial relationship. All right. Let us look at an example. All right. Okay, and once again, just a tip: you need to know the motor components to draw it and to label it. Right. That's very straightforward. It's straight out of the textbook. It's just know the sketch. Okay, now we're going to look at Barlow's wheel. All right, here's an example. Barlow's wheel. All right, loads of books use it, and we've got a magnet over there. All right, like so, and we've got another magnet over here, like so, and in between we've got over here a bath. Okay, and that thing is then full of mercury. No, we don't use mercury anymore. Okay, now we use a saline solution. Why do we do that? Because mercury is poisonous, very toxic to human beings. Mercury, once it's out and into the open, tends to flow. It's in rivers, and I believe its concentrations increasing in tuna fish. I don't know the details of it, but mercury is a very, very, very dangerous compound. So we use a very saline solution. All right. Then what do? We connect this solution. I'm going to do it with a blue line. I connect that up to a battery that side. Then I put something in between, back to black. It looks like, if you like, a ninja wheel or a star blade, or I don't know what you want to call it, something like that. It's mounted on a pivot. So this thing can spin. Okay? It's mounted somehow. All right? And over here, I'm going to just complete the circuit with blue. I'm going to go here now. Right, now what is happening here? You can see this thing is dipped into there. All right? So we've got a magnet, and let's say we've got north and we've got south over there. So we've got our north and our south. There they are. Now we've got the saw blade standing here, dipped into a pot of conductor down there. What is going to happen when we flick the switch? When we flick the switch, a current is going to flow, and the current is going to flow like so. As the current flows, it's going to flow and complete the circuit. Because the mercury is a conductor, so is the saline solution. So it completes the circuit. And what happens next? Well, we have an I flowing, we have a field. There's going to be a force, right? So it's going to make that, so you go north to south, and you can see if you go down, there's my field, the current is going down, the force is going to be out. So the force on this thing is going to be out. It's going to start spinning the wheel, isn't it? All right? So it's going to start spinning this wheel around. How do we do it? You look, you find out which way the current is flowing. There it goes, and there's your field. North to south current. The force is going to kick it out, right? It's going to spin that wheel. And here's another one, okay? What we've got here is we've got one that looks like this. Just put in another. Just change it to black. Come here. Okay. What they do is they put two conducting rods out here. All right. Let me draw this like this in 3D. And these rods are connected to each other, and what you've got then is you've got another little rod that sits on top of those like that. Okay, now what we want to do is we're going to see how this thing is going to move. So you'll put magnets above it. All right, let's say you put a magnet over there like that. All right, so let's say that's north and that is south. So there's our field. Then we run a current through it. Let's run the current this way. All right? So I is running that way and I is running that way. Which way is that rod going to move? Okay? So we say north to south, current that way. Okay? Can you see it? Okay? North to south. Here we go. There's north and south. So there's our field, right? Field is going down. North to south is the field. All right? Then the current is flowing that way, right? That way. So the rod is going to want to be pushed outwards in this direction, right? Because you know the current is flowing that way, north and south. Field, right? Current, and there you just do it like that. I would obviously have turned my book and said, right, there we go. Field north to south, current that way, the force is tending to roll the rod off the ends. Okay, that's another one that we can use. Now, generally speaking, that brings us to an end of the motor section, all right, and the forces experienced on a current carrying conductor. Once again, like I say, do draw it. Make sure your drawing is complete, that if they give you current, you know. If they give you which way it's moving and ask you which way the current is, okay, but it's an applied current, there will always be a battery in this. There's going to be a current creator. So it's if there's a battery, all right, if we have an external power source, therefore a current, okay, is imposed. It's a left-hand motor rule, right? So you then look for which two have I got. Do I know which way the current is going? Yes, I do. It's going that way. Do I know the north-south? Yes, I do. It's that way. Therefore, the force is at me. All right? Yes, you do have to look at it in 3D, which can be a little bit of a pain, so to speak. But you know what? Once you've gone through one or two, see, it's not the whole 3D bit starts to fall into place because this is 3D itself. Thanks for watching. What we're going to do next is we're going to talk about alternating current, DC current, and transformers and rectification. I'll see you in the next one. Cheers. Bye.